Modern financial crime operates through vast intersecting networks. Corporate fraud rings, money laundering operations, and cybercriminal syndicates move billions of dollars through thousands of digital identities and offshore accounts every single day. To execute these schemes without triggering alarms, illicit actors intentionally fragment their activities. They distribute their footprint across thousands of seemingly unrelated transactions, devices, and jurisdictions. Traditional tools rely on standard ledgers, linear transaction reports, and static spreadsheets. By design, these formats fail to detect coordinated, multi-layered attacks. A linear spreadsheet processes data row by row. It forces analysts to evaluate entities in isolation, masking systemic, coordinated relationships behind walls of text and numbers. Long before digital platforms existed, investigators recognized crime's structure is in physical connections. They used evidence boards to draw lines, mapping the ecosystem. To unmask modern digital syndicates, analysts must abandon linear data entirely and apply a methodology known as link analysis. This requires translating raw intelligence out of rows and columns and restructuring it into a mathematical graph topology. We are going to deconstruct how analyzing these nodes and clusters transforms isolated, seemingly harmless anomalies into actionable threat intelligence. By learning to identify the behavioral geometry hidden within the data, you can connect the precise dots that standard compliance software ignores. Detecting organized fraud no longer relies on scrutinizing individual transactions. It requires reconstructing the invisible architecture of the criminal network itself. This standard spreadsheet shows a clean, localized e-commerce transaction log. Every row appears legitimate to traditional fraud filters. To build a graph, we apply the first principle of graph theory, nodes. Nodes represent the discrete, individual entities within an investigation. Depending on the investigation, a node can be a suspect, a bank account, a shell company, or a specific digital device ID. The second principle is edges. Edges represent the behavioral or transactional links connecting those entities. An edge could be a wire transfer between two accounts, a shared IP address logging into two different profiles, or matching phone records. When we plot nodes and edges together, the intersection instantly flags coordinated behavior that the linear spreadsheet obscured. This is known as the cluster effect. When threat actors share identical credentials or device intelligence, they organically form these tight visual groupings within the graph. Standard Know Your Customer alerts miss these anomalies because they process user A and user B sequentially, blind to the shared infrastructure between them. The cluster proves these are not individual customers. They are a coordinated synthetic identity ring operating through a single drop address. By simply applying nodes and edges, the invisible infrastructure of a fraud ring becomes mathematically undeniable. Real-world investigations scale across millions of data points. When you graph raw intelligence without applying constraints, the screen is quickly choked by dense, overlapping noise. This visualization failure is called hairball overload. Connecting everything without filtering the inputs yields zero actionable intelligence. The root cause of the hairball is that raw intelligence is inherently noisy. Professional suspects intentionally fragment their identities. They use aliases, duplicate records, and varying alphanumeric IDs across different platforms to evade detection. To make the graph readable, analysts must execute a mandatory precursor to advanced analysis, entity resolution.
Entity resolution is the algorithmic process of stitching together multiple fragmented records referring to the same real-world target. The algorithm uses strict matching criteria and domain knowledge to confirm these merges with high confidence. Skipping this step creates severe intelligence gaps. Treating one real person as two separate nodes severs the connecting edges, leaving investigators chasing false leads. Conversely, incorrectly merging two different individuals creates a false link, corrupting the geometry of the entire graph. Entity resolution provides vital data sanitation. It ensures investigators are connecting the correct dots before they apply advanced mathematics to the network. In top-tier international financial investigations, analysts regularly ingest massive offshore data leaks containing terabytes of raw financial documents. Once a massive data set is ingested and resolved, the next objective is to locate the power players hiding within the complex geometry of the graph. To find them, investigators use centrality metrics, algorithms designed to quantify the exact mathematical importance and influence of every individual node. Looking at this network graph, we can calculate the first algorithm, degree centrality. Degree centrality identifies the hubs. These are nodes with the highest volume of direct connections, like a primary offshore shell company receiving laundered funds from 50 distinct subaccounts. But the most influential actor is rarely the most visible. To find them, we use a more sophisticated algorithm called betweenness centrality. Betweenness centrality identifies the nodes that act as the shortest paths between all other nodes in the network. This metric highlights the broker. On the surface, a broker looks like a low-level intermediary, but they are secretly the singular link bridging two separate extremist cells or corporate fraud rings. Identifying the targets is only half the equation. A static graph proves a relationship exists, but it cannot prove causality. For that, we require the final dimension of threat intelligence, time. Temporal analysis integrates timelines with spatial network topology. By tracking exactly when interactions occur, analysts can separate purely coincidental associations from highly coordinated causal attacks. Centrality metrics locate the targets, while temporal analysis proves their operational guilt. Together, they transform a static map into a devastating autopsy of a living syndicate. A modern investigator must master this entire sequence, ingesting unstructured data, running strict entity resolution, calculating centrality metrics, and applying temporal filters. Standard reports catalog past crimes. Link analysis enables surgical, proactive intervention. By definitively identifying brokers and hubs, law enforcement agencies can pinpoint the exact structural choke points of an illicit organization. Advanced graph algorithms can then run predictive models, forecasting exactly how a criminal network will attempt to rewire and adapt when that key player is removed. Without this technology, anti-money laundering officers and OSINT investigators will remain perpetually buried under false positives, limited by linear data blindness. Sophisticated fraud is engineered to look legitimate at the transactional level. Its illegality only exists in the relationships. For analysts facing modern digital threats, the ability to map nodes and clusters has become a foundational requirement. In an era of data overload, the truth is no longer found in the ledger. It is found by mapping the architecture of the shadows.